Hello friends. So in this video we are going to see how to solve the numerical when the mixing of air is given after the conditioner or after the cooling coil. In the previous video we have seen the numerical when the mixing was before the conditioner or before the cooling coil. So in the numerical statement, if anything is not mentioned about where exactly the mixing is done, by default you assume that the mixing is prior to the conditioner or cooling coil or before the conditioner or the cooling coil. So whenever there is a mixing after the cooling coil or the conditioner, they specifically it will be mentioned in the statement over there. Okay, so likewise this is the statement. We will go for the same conditions what we have seen in the previous video. So it is an air condition is to be designed for a room when the following data is available. Okay, so outside condition of the room is given 35 C dBT, 26 C WPT. Room conditions are given as 27 C dBT and 55% RS. So inside the room, I am going to maintain the temperature at 27 degrees Celsius, whereas the what you can say the relative humidity will be about 55%, and the sensible heat which is generated inside the room is 35 kilowatt. Latent heat is about 10 kilowatt. Here, in the previous example, the bypass factor was given. Instead of bypass factor, they have changed the statement over here and they have given the temperature of the air at the exit of conditioner or the cooling coil, which is nothing but the 18 degrees Celsius, and the 60% of the room air is recirculated and mixed with the 40% of fresh air over here. Okay, which is after the cooling coil. So very importantly, it is noted to be down over here, that is after the conditioner. We are supposed to calculate the RSHF, supply air condition, ADP and the cooling coil capacity in terms of refrigeration. Fine. So we'll go for this particular problem. As per our regular practice, the first thing you are supposed to draw the schematic of the system over here. So here assume that this is the room, okay, which is to be maintained at 27 C dBT and 55% RH, okay, 55% RH. Then I'm having the AC unit over here, which is having the cooling coil. This is the cooling coil, okay, this is the cooling coil. Then there will be the blower over here. Okay, fine. And this is nothing but the air will be supplied to the room from this particular point. Then you'll have the return air over here. Okay, this is the return air. Okay, it's a return air over here. Okay, now I am having the fresh air which is coming in from this particular side or the outside air basically. Okay, so what I'm doing, I'm mentioning the fresh air as the point number 1 or the condition number 1. Room I'm maintaining, let's set the condition number 2 over here. Okay, so obviously when the air is taken back from the room, the state of the air will be state number 2 only, that we have seen already in the previous example. Fine. Now as they have mentioned that the mixing is after conditioner, so this is the cooling coil, this is the cooling coil or the conditioner basically. Okay, one and the same. So the mixing is done after the cooling coil. Okay, so in previous case we have done the mixing before the cooling coil, however the mixing is done after the cooling coil. So I'll be having this particular return air coming down over here at this particular point. Okay, and this is the fresh air. Now inlet to the particular cooling coil, the condition will be the state number 1 only, because the fresh air is only passing. When this particular fresh air is passing over the cooling coil, obviously the state of the air will change, because there is the cooling of the air will takes place over here. So immediately after the cooling coil, the state of air will be different than the state number 1, and I am mentioning that state as state number 3. Now that air after cooling coil which is passing over here, which is at the state number 3, will be mixed with the return air over here which is coming from the room. Okay, so it is not like that whatever cooling is done, at the same state the air will be supplied to the room. No, because there is the mixing after the cooling coil, and the air will first, well, the fresh air which is passing over the cooling coil will be first cooled, and the state of that air will change from state number 1. So that state I am mentioning as the state number 3. Now the air which is at the state number 3 will be mixed with the return air which is at the state number 2, and obviously I'll be getting the different state over here than the 2 and 3, which is nothing but the state number 4 over here, which is nothing but the 4 over here, which is the mixing state, okay. So the 4 is nothing but the mixing state, 4 is mixing state, whereas 3 is nothing but the state after cooling coil, okay. So at a point 4, when the air is mixed, that point will be nothing but the supply point. So at point number 4 only, that air will pass to the blower, and from blower it will be given to the room over here. So the supply state of the air will be the state number 4 only. It will be the state number 4 only. Fine. So it's very important to understand this concept. What many of the people do, they will take the state number 3 as the supply state over here, which is the wrong one. Okay, that air is getting mixed with the return air, and the state will change over here. That is given over here. Now, what amount of what amount of air is passing over the cooling coil? That is nothing but the fresh air only. Fine, that is the fresh air only. Fine. Now we will uh, write down the given data over here, given data, and accordingly I will go on plotting the points. So the first thing, they have given the outdoor condition, that is 35 C dBT and 26 C WBT, 26 C WBT. Okay, so this particular point I will mark on the psychrometric chart over here. So it is 35 C dBT, it is 35 C dBT and 26 C WBT. Okay, so this is the 25 and this is 26. So somewhere over here I am having the point number 1. This is the point number 1, outside condition. Now the room design condition is 27 C dBT and 55% RH. So this is 26, 27. I'll go vertically upward. This is 50% RH. This is 55% RH. So here I'll have the the point number 2 over here. This is the point number 2. Fine. I will join the line 1, 2 over here. 1, 2, 2. Okay. This is the 1 to 2. Now I will mention the enthalpies at point number 1. At point number 1 the enthalpy is 85, and point number 2 the enthalpy is about this is 55, 57.5, about 58, let's say. Fine. So 85 and 58. So the enthalpy H1 is 85 kilojoule per kg of dry air, and H2 is 58. Yes, no, 58. Yeah, 58 it is. Fine. Okay, the unit is same, kilojoule per kg of dry air. Fine. Now, fine. I have got the point number 1. I got the point number 2. Now the next thing I supposed to get, that is the point number 3. The supply air, or rather the condition of air, it is given over here. The temperature of air at the exit of conditioner is 18 degrees Celsius. So what is the temperature given over here? That is nothing but the temperature of air after the conditioner, that is given. So that is nothing but the temperature of point number 3 they have given. Okay, so TD3 by default it is a dry bulb temperature you are supposed to take. It is given as 18 degrees Celsius. It is given as 18 degree Celsius. That is given over here. Fine. Now, okay, so we'll first go one by one. Now I am supposed to calculate the RSHF. Okay, so we know that to get the RSHF, so they have given the RSH over here, that is 35 kilowatt, and RLH they have given as 10 kilowatt. Fine. What is the data given? Yeah. Then 60% of return air. So 60% of return air is nothing but the, I can call this as the M2, let's say M2, which is nothing but the 60%, and M1, that is the fresh air, they have given us for 40%. M1 is nothing but 40%. It is 40%. Okay, so the total will be 60 plus 40 will be 100% will be supplied to the room. Fine. Now I will calculate the things one by one. So the first is RSHF. RSHF, we know that the formula RSH divided by RSH plus RLH. Okay, so that is what you can say 35 divided by 35 plus 10. That answer comes around to be 0.78. Okay, this is the RSHF, the first answer we have got. Okay, the second one what they have asked, that is the supply air condition. Now here the supply air condition, what is that point is, that is at what point the air is supplied to the room. This is nothing but the point number 4. So the second is nothing but the supply air condition, supply air condition. So that is nothing but the condition at point 4 that I supposed to get the things. Fine. Now obviously to get the supply air condition I need to make use of the RSHF line. We know that if you go over here, this is nothing but the RSHF line. This is the RSHF line. On the RSHF line I will be having the supply air point, that is the point number 4. Now I know that the procedure to draw the RSHF line. So I already calculated the RSHF, and then the next step is to connect this particular RSHF with the alignment circle. Okay, so we'll just follow one by one. So I'm having the 0.78 as the RSHF. So this is 0.7578 somewhere over here. Assume that this is the 0.78. Now I will connect this particular RSHF point. This is the RSHF. I will connect this RSHF with the alignment circle as I already discussed. The alignment circle is nothing but the dark point given on this particular psychrometric chart. So connect this particular 2 points. Okay. So this line is known to be the baseline. When I connect the RSHF with the alignment circle, this is the baseline. To this particular baseline, I need to draw one parallel line from the room design condition. So it is something like this. Okay, this is something like this. This particular line is known to be the RSHF line. This is nothing but the RSHF line. Okay, now if you see over here, this is the RSHF line which is starting from the room design condition and it is parallel to this particular baseline. Okay, so that is what we have done. Now the point number 3, the point number 3 is nothing but after cooling coil. This is the point number 3 which is after cooling coil. Obviously that point will be on the RSHF line only. That point will be on the RSHF line, because if you see over here in this particular diagram, uh, the cooling process in the previous case, the cooling was starting at the mixed point, that is nothing but the point number 3, and was ending at point number 4. So 3 to 4 is the process which was happening in the cooling coil, and this line is known to be the GSHF line. So wherever this GSHF line is intersecting to this particular RSHF line, I was getting the point number 4, which is nothing but the exit of the what you can say, the exit of cooling coil. Okay, exit of cooling coil. So the same thing here I have given, I am having the exit of cooling coil point, which is nothing but the point on the RSHF line. So that exit condition for the cooling coil they have given, and that is nothing but the point number 3. So the exit condition of cooling coil is given, that is point number 3, and for that the temperature they have given as 18 degrees Celsius. So what I will do, I will mark one line over here at 18 degrees Celsius. So 15, 16, 17, 18. Okay, somewhere over here, okay, wherever it will intersect the 18 degrees Celsius DBT line, I will get the point number 3. Okay, now if you observe carefully, over here in the schematic, on the cooling coil, the process, or what you can say, the points across the cooling coil are nothing but 1 and 3. So the cooling process starting at point number 1 and ending at point number 3. Cooling process starting at point number 1 and ending at point number 3. Okay, so if I want to show the cooling process on the psychrometric chart, obviously it is starting at point number 1 and ending at point number 3. So I will connect this particular line over here. Okay, obviously you are supposed to use the scale when you are doing the problems based on this. Something like this I'll be having. Okay, something like this. Fine. Okay, this is the line I have drawn. So here 1, 2, 3, that is point number 1, and point number 3, the line is the cooling process. If I extend this cooling process, okay, if I extend this particular, this is nothing but the GSHF line you can call. So if I extend this GSHF line and wherever it is intersecting to the saturation curve, I will get the apparatus dew point temperature. I will get the apparatus dew point temperature because this is the cooling process and this is the inefficiency of the cooling coil, and this particular length is nothing but the bypass factor. Fine. So this is nothing but the apparatus dew point temperature. So for this case, the apparatus dew point temperature what I am getting is about 11 degrees Celsius. Okay, so I am getting the ADP is about 11 degrees Celsius. So this point we are supposed to find out. Okay, that is one of the answer we are supposed to get. So this is the ADP of 11 degrees Celsius. Fine. Okay. So here very importantly, I need to get the point number 4, which is the supply air condition, which is nothing but the supply air condition. Now I supposed to get the point number 4, and the point number 4 is the mixing of the point number 2 and the point number 3, or the state number 2 and the state number 3. Okay. So in the previous case or by default case, if I go for the mixing, this is the cooling coil, then this is the return air from the room, which is at the state number 2. Here is the fresh air, which is at the state number 1, and the mixed state is the state number 3. In that case, I was getting the formula for mixed condition as M1 by M2 is equal to H3 minus H2 divided by H1 minus H3. That was the formula I used to get. Okay. Now this particular thing I'll be applying between the point number 3 and point number 2, because the mixing of air is between point number 3 and point number 2. Okay. So the same formula, only thing I will be apply between point number 3 and point number 2 over here. Fine. So here I am writing the formula. Okay. So what I am doing, I am just changing this particular point. Okay. I'll just draw a diagram over here for better understanding. This is the cooling coil. Okay, this is the point number 2 which is coming over here, and this is the point number 1. Okay, and the mixing is between 3 and 2. Mixing is between 3 and 2. So I'll be writing M3 upon M2. Okay, because 3 and 2 are getting mixed, so I am replacing M1 by M3 upon M2, which is equal to now H3. H3 is the mixed point, okay, or the mixed condition over here. So here the mixed condition is 4, so I'll be having H4 minus H2. H2 is nothing but the return air over here. Okay, so H4 minus H2 divided by H1. H1 is nothing but what? This H1 is nothing but I am replacing with H3 minus H4. H3 minus H4. Okay, so here you will have the M3 by M2 is equal to H4 minus H2 divided by H3 minus H4. Okay, this is what the what you can say, the formula to get the mixed condition over here. So the mixed condition is nothing but the point number 4 over here, the point number 4 over here. Okay, now here the M3, what is the value of M3? So I am writing the formula over here, M3 by M2, which is equal to H4 minus H2 divided by H3 minus H4. H3 minus H4. Okay, so here the M3 is nothing but what? That is the mass of air at point number 3. So what is the mass at point number 3? The same mass which is at the point number 1, because the fresh air which is flowing over here at point number 1 is the same air is passing over the cooling coil. Okay, so the mass at point number 3 and the mass of point number 1 is same. So M3 is equal to M1, so that is nothing but the 0.4 value divided by M2. M2 is nothing but the return air, which is nothing but the 60% of air. Okay, this mass is given over here. M2 is 60%, M1 is 40%, which is nothing but the M3. Okay, which is equal to H4 is unknown to me minus H2. H2 we already noted down, it is 58. It is 58 divided by H3. H3 is given over here, H3. Yes, we have not got the H3 value. So fine, go to the psychrometric chart, and with respect to point number 3, find out the H3, which is about 45 over here. Okay, you can see this is the H3 which is about 45. Fine, I am writing the H3 value over here. So H3 is 45. Okay, so I'll be having H3 is 45 minus H4 over here. Okay, so now okay, we will write down this formula. So 0.6 H4 minus 58, which is equal to 0.445 minus H4. Okay, just solve this. 0.6 H4 minus 0.6 into 58. Okay, you do the calculation. 0.6 into 58 into 58, that is 34.8, 34.8, which is equal to 0.4 into 45, 0.4 into 45, it is about 18 minus 0.4 H4. Okay, so now I'll take the H4 term on one side. So 0.6 H4 plus 0.4 H4, which is equal to 18 plus 34.8. So H4 is equal to 34 plus 18, about 52.8. It is 52.8. So this is the mixed state I have got. Okay, so I'll go back to the psychrometric chart, and 52.8 somewhere over here. This is 50, 55, 52.8, sorry. So this is 51, 52, 53. So somewhere over here I'll have the point. Okay, so I'll just mark this particular line, enthalpy line over here, something like this. Okay, so this is nothing but the H4. This is nothing but the H4. Now, on which line I should get the mixed point? Whether I should get the mixed point on 1, 2, 3 or between the 2 and 3. Okay, so that you can get it from the psychrometric chart. So between which point the mixing is done? That is between point number 2 and point number 3. Okay, so point number 2 and point number 3 the mixing is done. So obviously the point number 4 will lie between 2 and 3. It will lie between point number 2 and point number 3 only. Okay, so go back to the psychrometric chart. So here I am having the point number 2, here I am having the point number 3. So obviously the mixed point will be lying between point number 2 and point number 3. So that is nothing but wherever this H4 line is cutting to this 2 to 3 line, I will get the supply air condition. So that is nothing but this particular point, and that point is nothing but the point number 4. This is nothing but the point number 4. Now with respect to this point number 4, you get all the conditions, all the points. So here the dBT is about 23 degrees Celsius. WBT is about 18, 19, 18.5 something. Okay, so you can write down the answers over here. So supply air condition. Okay, I am writing here over here. Sorry. So supply air conditions. So that is at point 4, at point 4, point 4. So enthalpy at point 4 is 52.8. Already we have calculated. Then the dBT at point 4 is about 23 degrees Celsius. It is about 23 degrees Celsius. WBT at point 4 is about 18.5 degrees Celsius. Okay, you can go back to over here. So it is 18, 19. Okay, so it is in between, let's say, so it's 18.5. Then what else I need to get the W value? So it is W value about let's say 0.012, 0.01. Okay, so it is 0.015 over here, 0.0 sorry 0.0105 over here, 1 over here. Okay, about 0.0115. Okay, so that is the what you can say, W value is 0.0115 about. Then you'll have the relative humidity, RH or phi, you can write anything, you can write. So relative humidity at point number 4, this is what the curve, and the curve value is about 65%. Okay, so relative humidity you are getting about 65%. So these are what the conditions at the supply air point. Okay, that is the supply air condition at point number 4. Fine. The next thing. Okay, so now we'll see. So you have got the supply air condition. Next is ADP. Already we have got. So when you extend this particular 1 and 3 line, because the cooling is between 1 3. So wherever is the cooling process, you extend that particular line only, so that you can get the apparatus dew point temperature wherever it is intersecting the saturation curve. So it is 11 degrees Celsius. So ADP is 11 degrees Celsius. The next point, it is 11 degree Celsius. Fine. And then what they have asked is the cooling coil capacity in terms of refrigeration. Fine. So now to get the cooling coil capacity, I need to get what is the mass of fresh air. The percentage mass is given, but the actual mass of fresh air is not given over here. So I need to get the mass of fresh air. So to get the mass of fresh air, I suppose to get the mass of supply air. So when I get the mass of supply air, which is the 100% air, out of that 100%, the 40% is the fresh air, and that fresh air is only passing over the cooling coil. So whenever I supposed to calculate the cooling coil capacity, the equation for cooling coil capacity, so I am writing down over here cooling coil capacity, okay, which is equal to what mass is passing over the cooling coil? That is the mass of fresh air. Okay, it is the mass of fresh air. In previous case, the cooling coil, sorry, the mass of air which was passing over the cooling coil was M3. M3 is nothing but the dehumidified air, and which was the mixture of fresh and the return air. So it was the 100% of fresh air which was passing over the, sorry, 100% of air which was passing over the cooling coil. However, in this particular case, as the mixing is after cooling coil, only the fresh air is passing over the cooling coil. So that is the difference over here. You just understand the difference. So only mass of fresh air I supposed to take while calculating the cooling coil capacity. So it is what? The mass of fresh air, okay, mass of fresh air into the enthalpy difference across the cooling coil. So what is the enthalpy difference? What are the point across the cooling coil? That is point number 1 and point number 3. So I will have the enthalpy difference across cooling coil as H1 minus H3. It is H1 minus H2. So this is the cooling coil capacity. However, in this particular case, I know the H1 value, I know the H3 value, but I don't know about the mass of fresh air. Okay, so I am supposed to get the mass of fresh air. Mass of fresh air, and to get the mass of fresh air, I suppose to get the mass of supply air, or the total air, or the dehumidified air. Okay, so here if I get the total mass of air over here which is supplied to the room, I can easily get the fresh air, which is 40% of the total air. Okay, now we know that to get the mass of supply air or the dehumidified air, I suppose to consider what amount of heat is added over here, because the air which is supplied to the room, that air is responsible to take out the total heat which is generated inside the room. Okay, so that air which is supplied at point number 4 will absorb the heat from the room, and then it will be returned back. So initial state of the air is point number 4, whereas the final state is point number 2, and between this initial to final state, it is absorbing the total heat from the room. So I can write one formula over here, that is the total heat absorbed from room is equal to or rather yes, absorbed from the room is equal to total heat generated inside the room. It is total heat generated in the room. So what is the total heat generated in the room? That is, we know that it is nothing but the room sensible heat plus room latent heat. And what is the total heat absorbed from the room? So that is nothing but what mass of air is supplied to the room, what mass of air is supplied to the room into the enthalpy difference of the air, which is nothing but the initial state of air and the final state of air. So initial state of air is 4, supply air I am talking about. So initial state of supply air is point number 4, and the final state of supply air is nothing but the point number 2 over here. Okay, so here I'll be having the formula, that is the mass of supply air, which is I'm calling as the dehumidified air, MD, into the enthalpy difference across the room is H2 minus H4. Okay, so here MD is nothing but the mass of supply or dehumidified air. Most of the time it is written as MD for dehumidified air. Okay, please understand this is the dehumidified air. Okay, so here MD is equal MD into H2 minus H4. This is nothing but the total amount of heat absorbed in the room by the supplier, and which will be obviously equal to the total amount of heat generated inside the room. So this is, we know, this is 45 kilowatt, 35 plus 10, and H2 and H4 value, both the values we are having. From this I can get the MD, which is nothing but the RSH plus RLH divided by H2 minus H4. Okay, so here I get the MD is equal to, fine, I'll just calculate that MD. It is 45 divided by H2 value is 58 and H4 value is 52.8. So 58 minus 52.8. Okay, so it is about 8.65. It is about 8.65. It is about 8.65. Now what will be the unit of this particular mass? The unit will be kg per second. Kg per second. Now why the per second only? Because this relative, room sensible heat and room latent heat, you have considered in kilowatt. This value is in kilowatt. So kilowatt is kilojoule per second, whereas this value is enthalpies are in kilojoule per kg. It is in kilojoule per kg. So when you divide this kilojoule per second divided by kilojoule per kg, so RSH plus RLH, so this is kilojoule per kg divided by this, sorry, just a minute, I will erase this, it would be better. It's a kilojoule per second. Basically it's a kilojoule per second, which is nothing but the kilowatt, no? So RSH plus RLH is kilojoule per second, which is nothing but the kilowatt, divided by kilojoule per kg. So this kilojoule get cancelled. Finally I'll remain with the kg per second. Okay, so this mass will be in kg per second. Fine. So this mass is the dehumidified air mass. This is the mass of supply air. Out of this, 40% air is used as the fresh air. Okay, so if I want to have the mass of fresh air, which is equal to 40% of mass of dehumidified air. Okay, so this answer will be, now we'll have just multiply this term by 0.4 into 0.4, you'll get, so it is 3.46. It is about 3.46 kg per second is the mass of fresh air. It is the mass of fresh air. So once I get the mass of fresh air, I can easily get what is the cooling coil capacity. So I am writing down over here. Therefore the cooling coil capacity is equal to mass of fresh air into H1 minus H3. Now why 1 and 3? Because across cooling coil these are the 2 points. Okay, so it is 3.46 into H1 is 85, I hope, correct, and H3 is where somewhere we have written the H3 value. H3 value is H3, fine, where you have written H3 value, fine, we'll take H3 over here. It is 45, fine, it is 45. So 85 minus 45, that is what? 85 minus 45. Okay, so this is the cooling coil capacity. Okay, so 3.46 into I'll have 85 minus 45. Okay, so it is 138.46, 138.46. Now the unit, what is the unit of this? That is kg per second. This is kg per second into, what is the unit of this? This is kilojoule per kg. So this kg get cancelled. Finally I will remain with kilojoule per second. So this kilojoule per second is nothing but the kilowatt. This is nothing but the kilowatt. I am supposed to have this particular answer, cooling coil capacity, in terms of refrigeration. So I will divide this particular term by 3.5. I'll divide this term by 3.5 because 1 TR is equal to 3.5 kilowatt. Okay, by using this particular relation, I will get this particular value in terms of refrigeration, which is coming around to be 39.56 tons. Which is nothing but 39.56 tons. Okay, so now here if you see, and if you compare this particular cooling coil capacity with the previous case, here you'll have the cooling coil capacity larger. We require more tonnage over here to cool the air because I am using directly the fresh air and passing over the cooling coil. Okay, So I'm having outside air condition to the condition number 3. Okay, so that much of temperature difference is there. Here the temperature difference is more, and hence I require more cooling coil capacity, whereas in the previous case I was initially mixing the return air with the fresh air, and the return air percentage was more, so mixed condition was close to the return air condition. Okay, and hence the temperature difference across the cooling coil was less, and hence I was having less what you can say the turns requirement for the cooling coil, whereas here I am having the more turns of requirement, because I am using the fresh air directly and it is passing over the cooling coil, so the temperature difference is more over here. So that is how you supposed to design the system. Okay, but this may be the what you can say the specific requirement, and hence we are passing over the we are directly passing the fresh air over the cooling coil. But most of the time you will find the return air and fresh air, they will mix first prior to the cooling coil, which is shown over here, and that mixture will be passed over the cooling coil, so that the turn requirement will be on the lower side, because the temperature difference is on the lower side. For example, assume that now at point number 4, what is the supply condition I am getting, the dBT I am getting, let's say at 23 degrees Celsius. Okay, so in both the cases you supposed to maintain 23 only over here, and here also 23, but however here the inlet condition is 35 degrees Celsius, 35 to, so here 35. Okay, 35 to 23, and here the mixed condition, you are mixing the 27 degrees Celsius air with the 35 degrees Celsius, and the 27 degrees Celsius percentage is more, so obviously this particular temperature will be close to 27 degrees Celsius. So let's say it's 29, assume it is 29, so you are cooling from 29 to 23 in this case, whereas in this case you are cooling from 35 to 23. So obviously here I will require the more cooling capacity, because the temperature difference is more. Okay, so this is how you have to analyze the problem as well. Fine. So this is what about this particular problem, how to tackle when the particular mixing of air is after the cooling coil. You are supposed to go with this particular steps. Fine. I hope you understand the problem. If you are having any doubt in this particular problem, you can write into the comment. I will try to solve those. Thank you.